For part G, we were going to assume that the call to B takes constant time. And so really the work of this function is two recursive calls, each with argument n over 2, and then a for loop. And so again, we can apply the same formula that we've been doing. So I equals 0 to height of the branching factor to the I times the amount of work per node per level. Okay, so if we look at the branching factor, it's 2 because we're making two recursive calls, and so we know that BF is 2. And then again, we can draw out the recursion tree. So we start at n, we go to n over 2, and then each of them is going to call n over 4 twice. And so we have something that goes like this, and it will continue on infinitely. Or sorry, not infinitely, but until it reaches 1. And so the height of this tree is actually going to be log n for the same reason that n over 2, n over 4, all the way down to 1. Whoops, you can't really see that, but this is also equal to log n, right? And so our height is log n, and then the amount of work we do per node is really just in the for case, so the for loop case. So in this case, we're going from 0 to n, and we're multiplying by 2 each iteration, which means that we're doing log n amount of work. And again, we need to make sure that n is really in terms of the input size of each node, and so that's going to be n over 2 to the I. So plugging everything in, we have I equals 0 to log n of 2 to the I times log of n over 2 to the I. And this again seems kind of scary to compute. And so one thing that we can do is employ a trick of having a simpler looking upper bound, in which case it would look like this, just log n, right? And we can prove that this relationship between the left-hand side and the right-hand side is true because log of n over 2 to the I is always going to be less than or equal to log of n. And so we can take out log of n outside the summation because it doesn't depend on I. And so this is really going to be log n times the summation, I equals 0 to log n of 2 to the I. And if we expand out this entire summation, this is going to be log n of 1 plus 2 plus 4 plus all the way to 2 to the log n, right? But again, assuming that log is base 2, this is really just going to be n. And so we have this 1 plus 2 plus 4 plus all the way to n series, which is a very commonly known series that sums up to a linear amount. So in this case, it's just going to be n. And so our end result is going to be n log n. Okay, and notice that this is both for worst case and best case because there's really no way. This is actually for worst case because we actually have this call to B of I, where if this returns true, we can just break out of the for loop. And so our worst case, it would be theta of n log n, in which case B of I always returns false. And our best case is when B of I always returns true. And so we always break out of the function doing a constant amount of work per node. So this would be constant amount of work, which means that is just theta n. And the way that I got theta n is by just plugging in, basically substituting this for 1, right? And so really we're just solving this part. And again, we said that that was linear.